Yo, my people, you know it's day 17, 16, 17. Let me check. Whoa, we have to run that back. We gotta run that back. We gotta run that back. Yo, my people, you know it's day 16. Running with Dappa. We're indoors today because outdoors is rough. And today we're gonna be basically walking because I ran a half marathon on day 15. Can you believe it? Right now my legs are killing me. But as you know, we have the fit Jamaica shirt, grey shorts, knockoff Nike Air as the pants, and my brown lock sack and my pink Kish headphone. But we're here. Anyways, y'all. So basically, I decided to, you know, we did the day 15, we ran for an hour. And then afterwards, I was like, yo, let me just continue an hour. And then I got a few 14K. I'm gonna say, yo, because I was just listening music and browsing the internet and all that stuff while I was running. And then around the mall. And then something just tell me, say, yo, let me check up how much is a half marathon. And I saw that it was 21Ks. So if it was 21Ks, that means I could have just like, you know, go take a look and see if I could like yeah, it would just be 6K, 7Ks left. That's 14. So alright, let me just continue. And yo, that was one of the hardest experiences that I've ever done. Because when I was at about 3K left, my legs were just giving way. Here is still hurting me, my hip, my body. Yeah, I kind of just feel like I'm in a lot of pain. But at the end of the day, we did what we have to do. And I'm very happy with how it turned out. I'm not happy with how the first part of the video turned out. It looked like I was, it was dark because I ran into the trail and all that, but I'm fine with that. So today the plan is to just chill, play some music while I walk. I play it as background music. You can use this as a tool to run yourself alongside me and just bounce with some music. Let me know what type of music you want to hear on those days. Sometimes I'm gonna go to the coding stuff. Sometimes I'm gonna do a lot of vibes. Sometimes I'm gonna be chill. Today's a little bit chill because my feet are killing me, so I can't do a slow jog. That hurts. Maybe I push through. Maybe I walk. Let's see. Yeah, it's gonna be tough to run. Forgot to turn on my watch. But anyways, y'all, we're here, we're outside, we're having fun, and we're trying to get our steps and trying to get our heart rate at zone 2. We're gonna turn on this, and of course, you know, fish in the plant. Oopsie. Fish in the plant. You know what I mean? Stand is not working. Put it under this. That works. Alright, people. So what y'all been up to? Let me know in the comments. I'm at 7 minutes. We're gonna go for an hour. We might start running. I'm in a lot of pain, bro, from this half marathon thing. So we outside anyways. We're just happy that we did what we needed to do, y'all. Actually, let me check how much minutes are. I think let's go. Oh, 5 minutes and 55 seconds. Okay, cool. We got that. And we're starting off now with this one. 36 seconds on the watch, so that means I'm gonna go 55 minutes on the watch. I'm in zone 1 right now. But we're very chill today, y'all. We're not too full of too much energy. We are recuperating. This is a restful run. Okay, y'all, I'm gonna play some videos regarding some coding stuff so that y'all can be entertained. So you guys now remember we did some Fibonacci, some dynamic programming and some questions like that. Now we're gonna be doing some sorting algorithm. Oh, I did actually privately look at some sorting algorithm stuff, but I'm gonna look at bucket sort today.
Now it's time for another sorting algorithm called bucket sort. Are you surprised at how many sorting algorithms there are? You should be, because there's a lot more sorting algorithms that we're not even going to cover. But bucket sort is definitely worth covering because it's unique in that actually it can run in big O of n time, even in the worst case. So it's super efficient. So why did we even bother learning the other algorithms that run in, let's say, n log n time? Well, that's the downside of bucket sort. It's very rare that you're able to use bucket sort. It's sort of a forbidden technique which very rarely gets to be used. And that's because there needs to be certain constraints for the problem. In this case, the constraint is on the specific values that we are sorting. We're only allowed to use bucket sort if we're guaranteed that all the values that we're sorting fit within a finite range. So in this case, the only values we have are 0, 1, and 2. So we can say that the range of values is in between 0 and 2. Now, typically when you have an array of integers, usually the integer is bounded, like it might be a 32-bit integer or a 64-bit integer, and therefore we would have a range, right, like -2 to the power of 32 approximately, all the way to 2 to the power of 32 positive approximately. So we could say that that's our range. But that's a really, really big range, and that usually doesn't qualify for bucket sort. We're talking about generally smaller ranges, but in this case, we have a very small range, 0 to 2. I mean, you could have a lot bigger, 0 to 100, or maybe even 1,000, or 10,000, or 100,000, right? Like that's still relatively small. Back to our example, we have this constraint, so we can use bucket sort. So what are we gonna do? Well, for every single value in our range, in this case we have a 0, a 1, and a 2, we're going to create a bucket for every single value. That's where the name bucket sort comes from. So for 0, we're going to have a bucket, for 1, we're going to have a bucket, and for 2, we're going to have a bucket. So I have an array of 3 values. This is where each of our buckets is going to go. So each of our buckets is basically a value itself. So for this array, we have indexes 0, 1, and 2. So conveniently for us in this case, the 0 is going to map to the 0 index, 1 is going to map to the 1 index, and 2 is going to map to the 2. It's not necessarily always going to be the case like this. For example, instead of having a 2 here, we could have had, let's say, a 4. In that case, we would just, arbitrarily put the 4 in this spot. The point is, for each of these values, we have it mapped to a position, and what this position is going to represent is the number of zeros that we have. So what we're going to do here is go through this array, count how many zeros we have, and then put that count over here. So we know we have 2 zeros, so 2 would go over here. Here we're going to put how many ones are in the input array. We just have a single one, so we're going to put 1 here. How many 2s are in the array? We have 1, 2, 3, so we're going to put a 3 over here. Now, what would be the time complexity of counting all of these? You might think we have to pass through the input 3 times, 1 for each of our buckets, but we actually don't. Let me just quickly show you how we would actually go about counting these. It's mostly straightforward. We would have an index, right, like I, starting at the beginning of the array. And actually just jumping into the code really quickly, assuming we're given an array like this, which looks exactly as our example, and we have our counts, we're going to have an I pointer going from the beginning of the array all the way to the end. And what we're going to do is take this value 2. Well, first let's talk about how we're going to initialize our counts. Initially, we're going to say we have 0 zeros, we have 0 ones, and we have 0 twos. But as we iterate, we're going to get to the first value, we have a 2. So what we want to do is increment our number of 2s. We can do that by going to counts at index 2 and incrementing it by 1, because we know that 2 maps to the index 2. That's convenient for us. It might not necessarily be the case, but we could have some kind of mapping. So we can increment this by 1. And we're going to continue to do that. We're going to go here. We're going to end up incrementing our number of 1s. We're going to go here. We're going to increment our number of 2s again. We have 2 2s. We're going to go here. We have 1 0. Now we have 2 zeros. So increment the number of zeros to 2. And then we have our last value, which is a 2. So we increment the number of 2s to 3. So now just cleaning this up a little bit. After counting, we know we have 2 zeros, 1 1, and 3 2s. Now it's time for the second portion of the algorithm where we actually sort the array. So the reason we counted each of these values is because we know when we take this array and we sort it, of course the zeros are going to go at the beginning, then the ones, and then the twos are going to go at the end. We know the output is going to look something like this. So if we could just know how many zeros to put at the beginning, then how many ones to put, and then how many twos to put, and of course, maybe we would have some threes as well and have some fours, but in this case we don't. But if we can do that, then we can fill this in without having to swap these values around. Every sorting algorithm we looked at so far would swap values. We have a 0, we know that's going to go at the beginning, so we swap it with the beginning. But bucket sort does not do that at all. By the time we get to this point where we have counted all of the values, we don't even need the input values at all. We don't even care what these are anymore. We're just going to start overwriting them, and we're going to do that with a couple loops. So our outer loop is going to have a variable called n, which is going to iterate through every position in counts. So we're going to iterate from 0 to counts.length. So we're going to go from here to here to here. By the way, this is just pseudocode. It's not necessarily syntactically correct, but this is the main logic that any program in any language would follow. So we have n, and then in the inner loop, we're going to have a second pointer. Let's call it j, which you can see j is not actually being used anywhere, but we're just using this pointer to iterate this many times. So let's forget about j. Let's just see how many times are we iterating. Well, 0 to counts of n. So basically what I'm saying here is we're going to iterate this many times. At this point, our n pointer is here, so we're going to iterate 2 times. Now, what exactly are we going to do? We can see we have a third pointer, I. This is important because I is going to tell us where to fill in the value. Initially, I is going to be at 0. Of course, we would want to fill in starting from the beginning. So we're going to fill this position with whatever n happens to be. We know n is the value, 0 is the value, so we're going to put 0 over here. And how many times are we going to iterate over this loop? Well, whatever counts of n is, 2 times. I hope it's starting to make sense now. We have 2 zeros, so we're going to put 2 zeros at the beginning of our array. So we're going to increment I now to be over here. We're going to put a 0 over here. And then our inner loop is going to finish executing. And then we're going to go back to the outer loop. Now our n is going to be incremented. Our n is going to go over here now. So now how many times are we going to execute the inner loop? Well, n is at 1. How many ones did we have? We only had a single 1. So now with our I pointer over here, we're going to fill in a 1, and then we're going to increment our I to be at the next position. And this loop only executed a single time, and then our n is shifted here. So we're going to put a 2 over here. We're going to increment our I. We're going to put a 2 over here. We're going to increment our I, and we're going to put a 2 over here. We just ran that 3 times. So our inner loop is finished executing. Now we're going to go to the outer loop, and end up shifting our n one more time, now it's out of bounds. That's how you know we're done with the outer loop, we're done with the algorithm, our array is sorted, and we can return it. So now the question is, why is this algorithm big O of n? Because don't we have nested loops over here? Well, as I just showed you, this nested loop portion, how many times is this nested loop portion actually going to run? Just because we have nested loops does not mean the time complexity is n squared. We know that this I pointer is going to be incremented every time the code actually runs and evaluates. And as I just showed you, our I pointer is going to start at the beginning and then keep being incremented until it goes out of bounds. How could that possibly be n squared? Just because we have nested loops does not mean it's n squared. Because the first time the loop runs, it ran twice. Then the next time it ran once, and the next time it ran 3 times. All of those are always going to total up to be n, because of course we're only going to have n values. These are just the counts, and then we're going to put the values into the array, which of course is of size n. So what I'm saying is this nested portion is big O of n time complexity. Of course, we did have to iterate through the input one time before that over here, and the time complexity for that was also big O of n. Well, adding these together would make the time complexity big O of 2 times n, which we know reduces to be O of n because we don't care about constants. So the overall time complexity is big O of n. In this case though, we are using a bit of extra memory. We're using an array, but what's the size of this array going to be? It's going to be whatever the range of values happens to be, the possible range of values. And we know, in this case it's from 0 to 2, but it could be, from some constants n to m, something like that. And as long as it's some fixed size that isn't like insanely large, we assume that this is a constant, so therefore the extra memory we're allocating, in this case, it's big O of 3, but it's going to be some constant c, and we know constants reduce to big O of 1 space complexity. But I do want to mention that this is sort of a forbidden jutsu. It's very rare that you're going to actually use bucket sort. The only time you're probably going to end up using it is in an interview, to be honest. But there definitely are some practical applications, and maybe you'll come across them at some point in your career. Now, the last question for us to answer, is bucket sort a stable algorithm? Well, the answer is pretty short, no, and I think in this case it's actually pretty clear why. When we overwrite the array, we're not even caring about, which 2 came first, because we just counted that there were 3 2s and they're all going to go in the last 3 positions. We don't care which one goes where. In fact, we're not even swapping the values anyway. We're just overwriting them. So it doesn't preserve the relative order at all. So bucket sort is definitely not a stable sorting algorithm. But if we wanted to, technically we could make bucket sort a stable sorting algorithm, because for example, as we count the 2s, we could preserve that somehow. For example, if this was actually a linked list instead of an array, as we count the 2s, instead of just counting them, we could have actually taken each 2 and added it to a linked list. So we would have a series of 2s like this, where this one would have been the first one, this one would have been the second, this one would have been the last. And then when we finally build the result, we would have put them together something like this. Now, this isn't super important to understand. I'm just mentioning it anyway. It's pretty rare that bucket sort is used on anything other than an array anyway. So now lastly, let's compare our sorting algorithms. So bucket sort, which is generally an unstable sorting algorithm, runs in the worst case in big O of n time, but it's a little bit misleading. Remember I said this is sort of a forbidden jutsu. Most likely you won't be able to run bucket sort on the input that you're given. But if you ever are given an input where bucket sort can be run, don't ever use any of these other algorithms, because they're not going to be as efficient as bucket sort. If you are given an input where the values are within some specified range, always use bucket sort. Otherwise, if you're given just a general input, most likely you will end up using either merge sort or quick sort. I think merge sort is generally more common.
Nice. So time complexity. You may be looking at a nested for loop and immediately go, oh, that's n squared, but that's not quite right. Let's do some analysis. We know for the first loop, we're performing n steps since we're going through all the elements and counting frequency. The first for loop will run n times, where n is the length of the counts array. However, the inner loop will only run until counts n, which means it is different every time. The first time it will be 2, and the next time 1, and then the other time 3. Therefore, our algorithm belongs to O of n. Since we are overwriting the original array, there is no way to preserve the relative order of the values. There is no swapping that takes place either. Hence, it will be unstable. Okay, we're gonna do search. We know search already. Binary search, you go from the end to the front. I mean, from front to the end. Mark a middle. If it's less than the middle, go to the middle or the left side. If it's right, go to the right side. Left, fine. It has to be sorted. It is of log n time complexity. You have to make sure that you are checking off by one issue. So mid, the target is greater than mid, you go right. If it's less than or equal to mid, you go to the left. To go to the right, you have to set your left pointer to mid plus 1. To go to the left, you set your right pointer to mid minus 1. If not, you say return mid, i.e. if it is equal to mid. And let's say the binary search, if it's not there, return false. If it is there, return true. Okay, we're gonna do one named search range because we did the search one just now. Oh wait, binary search. Search a 2D matrix. Okay, let's watch that one.
Everyone, welcome back, and let's write some more Neetcode today. So today let's solve search a 2D matrix. And I really like this problem because it's not one of those problems that you need a fancy trick for. You can actually solve this problem just by using logic. So we are tasked with creating an efficient algorithm for searching for a single value in an m by n matrix. The matrix has two properties. In every single row, the integers are sorted from left to right, and the first integer of each row, for example, this 10, is always going to be greater than the last integer of the previous row. So greater than this one. So in other words, we know that each row is sorted, and then the next row is going to be greater than that. So technically, each value in total throughout the entire matrix is going to be in sorted order. So that's pretty good. In this example, we were given a target 3, so if we search for the target, we will find it right here. So then we can return true that it does exist. If it does not exist, then we simply return false. So how can we solve this problem? The key word here is create an efficient algorithm. What would be the brute force? Of course, we could do an algorithm O of m by n, basically by searching every single value in the input array, right? That's a pretty easy algorithm to do on a two-dimensional matrix, but can we do better? Of course we can, because they gave us a couple properties that this matrix has some sorting already applied to it. Assume that we just had a single row, like forget that we had a matrix. If we just had a single row like this one, and we know it's in sorted order, do you know an algorithm that can search for a target value in a sorted array? I know of one called binary search, right? And how efficient is binary search? Well, let's say the size of this array is n. We could do a binary search in log n time, right? But of course, we know that we actually have m different rows, right? So let's say we ran a binary search on every single row until we found the input. target value, right? What would the time complexity be? Well, log n multiplied by m is going to give us a solution like that. So that's using the first property, knowing that each row's integers are sorted. And this is a pretty good solution, but can we do even better than this? I'll give you a hint. We're definitely going to have to use this second property that they told us. Each row itself is actually in sorted order, as in we know that the values in this row are going to be smaller than all of the values in this row, and all of the values in this row are going to be smaller than all of the values in this row. So can we use that property to, instead of searching through every one of these m rows, maybe we can actually do a binary search just to figure out which one of these rows to search in the first place. Because for example, if we're looking for a target value 3, let's take a look at this row. This row could have any values between 10, which is the lower bound, and between 20. So obviously the target value 3 is not going to fall within that range between 10 and 20, right? So then the question is, okay, if the target value is definitely not in this row, we can cross this row out. But then which direction are we going to go? Are we going to look at the row above it, or are we going to look at the row below it? Of course we would want to look at the one above, right? Because above, the top row is going to have smaller values than the bottom row, right? So when we cross this row out, we can also say that, let's cross this row out too, because of course this row is going to have greater values. That's how the binary search is going to work, to even figure out which one of these m rows then the leftmost value in the array, aka the target value, is smaller than the smallest value in this row. In that case, we need to look at rows with smaller values. So we're going to shift our top pointer. Actually, I think I just did it backwards. So when we look for larger values, we actually want to take our top pointer and then shift it down, because when you go down in the matrix is when you actually get larger values. And if we want to look for smaller values, we're going to take our bottom pointer and then shift it up. In that case, we would want to set it to be row -1. So that's the case if the target value was either too big or too small. If neither of those evaluates to true, that means that the target value is actually does fall within this current row. In that case, we just want to break out of this while loop. And then we can do the second portion of the binary search. Now, it's possible that if we did not break out, maybe we just created an invalid condition where we figured out that the top and bottom pointers are invalid, right? Then our while loop would stop. And what that would tell us is that we crossed out every single row in the matrix and none of the rows contained the target value. In that case, we have to return false immediately. So basically, if not top is less than or equal to bottom, that means that none of the rows contain the target value, and then we can just immediately return false. If that's not the case, then we're going to move on to the second binary search portion, and we're going to run binary search on the current row that we found from the top and bottom pointers. So let me just copy and paste that. This is the row that we're going to run binary search on, and we're going to have a couple of pointers left and right, which is going to be 0, and columns -1, because that's going to be the rightmost position in the row. And we're going to do pretty much the exact same thing that we just wrote above, a second binary search while left is less than or equal to right. Let's compute the middle point. We can do that by taking left plus right divided by 2. And now we'll do the same thing. So if we find that the target value is greater than the value in this target row at position middle, that means we have to search towards the right of the row. We have to search towards the right of this middle point, in which case we'll say our left pointer is going to be m plus 1. We're going to search towards the right. Else, if the exact opposite was true, then we want to search towards the right, so we can shift our right pointer to be mid -1. And else, the last case is if we actually did find the target value. In that case, of course, we can return true. Now, if this loop exited, but we never returned to true, then outside of the loop, then we have to return false, meaning that we never found the target value. Okay, I just forgot that when we were copy and pasting, I forgot to change this condition. So the first one, of course, is if target is greater. The second else if is if target is smaller, then we want to shift the opposite pointer, and that is the entire code. So you can see that it's pretty efficient. So I hope that this was helpful. If it was, please like and subscribe. It supports the channel a lot, and I'll hopefully see you pretty soon. Thanks for watching.
That was cool. So my GoPro died and got too hot. So I know for future, did damn before when I was doing it on 1080p, but it died today because of the 2.7K video quality. Kind of sad, but so it goes. I'm at 46 minutes right now. Watch another video. Now we're at binary trees. Yay.
Now let's move on to probably the most complicated data structure we've covered so far, which is binary trees. We're actually going to be using pretty much every topic we covered so far to understand binary trees because there's a lot of complexity to them. To start with, we're just going to understand the structure of binary trees. They're similar to linked lists in that we have nodes which have some kind of value. I mean, it could be a character, it could be an integer, or it could be a string, it could be an object. There could be anything contained in the value of this node. To keep it simple, let's assume we have integers, and let's say we have the integer 2 here. And we know that these nodes are no fun unless we have some pointers to connect them together. With binary trees, as the name implies, binary, which means 2, these nodes are going to have 2 pointers. But with linked lists, we had some next pointers and previous pointers for doubly linked lists. So it's kind of similar to that in a sense. It's similar to a doubly linked list node. But in this case, we draw the pointers typically down. And that's because there are some relationships with these nodes. We call this the left pointer and the right pointer. And when we have a pointer like this that's connecting it to another node, let's say a 1 value here, that node is also going to, of course, have a left and right pointer. Now, these nodes have a relationship. It's not like a linked list where nodes are just connected left and right. We say the relationship between these nodes is that this node is the left child of this node. So there's a relationship called the child relationship. This is a child of the parent node. So this node is considered the parent node of this node. But as I said, since this is the left child, this node could also have a right child. Let's say the value is 3. This node is also a child of this node, and this node also has the same parent as this node. Both of these nodes have the same parent node. And what about these 2 nodes now? Well, this node does not have a left child as of now, and it does not have a right child either. We can assume that these pointers are pointing to some default value of null. They're not actually pointing at any real nodes. And when we have nodes like these that don't have any children, we call these leaf nodes. So this would be a leaf node, and this would also be a leaf node, but What if for this node we actually did have a child over here, let's say it's 4, then this node would no longer be a leaf node. This node would be a leaf node. It doesn't have any children, but its parent node over here does have a left child, so it's not a leaf node. With binary trees, we're always guaranteed to have leaf nodes. If we start at the top of the binary tree, which by the way is called the root of the binary tree. The top node is always called the root node, whereas, the bottom nodes are called leaf nodes. And these are, terms that come from trees in general. Trees have roots. Trees also have leaves. But the interesting thing here is you might have noticed the root goes at the top and the leaves go at the bottom, which is kind of the opposite of a regular tree where, let's say you had a tree that looks something like this, where the roots would be at the bottom of the tree and the leaves would be at the top of the tree, but we know that that's not the case here. So that's just an interesting point about trees. We kind of draw them upside down, but these are important terms that are used with binary trees. Of course, every tree is only going to have a single root node, but it could have multiple leaf nodes, and it's guaranteed to have some leaf nodes. But why is that the case? I mean, what if I had from every single leaf node, one of the pointers just pointed back up to the root? I mean, we had that with linked lists, right? In some linked lists, I talked about you could have a cycle. But when it comes to binary trees, we are not allowed to have cycles. That's part of the definition of a binary tree. We're not allowed to have cycles. So since binary trees can't have cycles, that's the same reason why two adjacent nodes like these can't be connected. We can't take the right pointer of this and then connect it to that. That would sort of form a cycle. Now, technically, this here does not form a cycle because each of these pointers connecting nodes can only be one way. We can only go along it in one direction. But the definition of a binary tree, we say that it doesn't form any cycles, basically assuming that these pointers are not directed. Right? Assuming we could go both ways, there should not be any cycle in the graph. So therefore, we can't connect these two nodes together. By the way, nodes like these that have the same parent are considered sibling nodes because they share the same parent. So, that's where this word comes from, sibling, like brother or sister. And I guess it's hardly worth mentioning, but all the nodes in a binary tree have to be connected together. We can't just have some random node over here, which isn't connected to the rest of the binary tree, and then call this one cohesive binary tree. It's not, because every node has to be connected. We can put the node here where it's actually connected to another node, but we can't just have it floating randomly. All nodes have to be connected to each other. Now, there's another property of a node in a binary tree, which is called the height property. And it's mostly straightforward. First of all, we would measure a single node. We can say and connect it to that. That would sort of form a cycle. Now, technically, a cycle of roots, leaf nodes, node over B, pointers are point. Node is also pointers are not directed. Right? Assuming we could go both ways, there should not be any cycle in the graph. So therefore, we can't connect these two nodes together. By the way, nodes like these that have the same parent are considered sibling nodes because they share the same parent. So, that's where this word comes from, sibling, like brother or sister. And I guess it's hardly worth mentioning, but all the nodes in a binary tree have to be connected together. We can't just have some random node over here, which isn't connected to the rest of the binary tree, and then call this one cohesive binary tree. It's not, because every node has to be connected. We can put the node here where it's actually connected to another node, but we can't just have it floating randomly. All nodes have to be connected to each other. Now, there's another property of a node in a binary tree, which is called the height property. And it's mostly straightforward. First of all, we would measure a single node. We can say the height of a single node like this one is 1. We say that because there's just a single node, so we call it to be 1. The height of this is 1. It doesn't have any children. But for a node like this one, where it does have some children, we measure the height starting from this node, going down to the lowest descendant of the node. This is another key word. Descendant basically means for some node, such as this one, a descendant of this node would basically be any child or any other node that comes beneath that one. So basically for the root node over here, every node in the tree is a descendant of that node. And it's also worth mentioning that another key word used is ancestor, which is straightforward, just like descendant. It would basically means for some node, such as this one, a descendant of this node would basically be any child or any other node that comes beneath that one. So basically for the root node over here, every node in the tree is a descendant of that node. And it's also worth mentioning that another key word used is ancestor, which is straightforward, just like descendant. It would mean that this node, any node that came basically in the parent chain of this node. So this is the parent node. This is sort of the grandparent. And basically any node going up that chain would be considered an ancestor of the original node. This node doesn't really have any ancestors because it doesn't have any parents, but it does have a bunch of descendants. But going back to what we were talking about, the height of this node is starting from this node, going to its lowest descendant, which in this case, it only has a single descendant. What's the length of the path? Or in other words, what's the number of nodes starting from here going to its lowest descendant? Well, we can count 2 nodes. So we say the height of this node is equal to 2. Can you tell me what would be the height of this node? Well, we could go down to the right. This forms a path of 2. That's the longest path we can form going on the right side. On the left side, we can form this path, which has 3 nodes in it. Clearly 3 is bigger than 2, so we say the height of this node is equal to 3. I do want to mention that in some cases, people measure the height of a single node to be 0. So that would mean the height of this node is equal to 0. That would mean the height of this node, which we said was 2, would actually be measured to be 1. I don't prefer that way of calculating the height, but I just want to mention that sometimes in some textbooks and courses, people do that. So don't be too surprised if you see it, but the important thing here is whether we start at 0 or start at 1, the important thing is how you would actually calculate it. And I've illustrated to you that starting at the node, the height would basically be measured by finding the longest path going down. We have the opposite concept of height, which is depth. So what would be the depth of the root node? Well, it's measured as the path from here to the root node, and this is the root node, so we could say that the depth of this node is 1 based on how I like to calculate it, but some people would say that the depth is 0. What about for this node? What's the depth of this node? Well, what's the path from here up to the root node? Well, it contains 2 nodes, so I would say that the depth of this is 2, but some people, instead of counting the nodes, they would count the pointers connecting the nodes together, and in that case, you could call it to be 1. What's the depth of this node? Again, it's going to be the way I calculate it, it would be 2 because we have 2 nodes here. What about the depth of this? Well, it's going to be 1, 2, 3. So the depth of that node is 3 because that's the path from this node up to the root. So these are a lot of the key concepts that can come up when talking about binary trees. So I wanted to introduce you to some of the basics. So it wouldn't be complete if we didn't at least talk a little bit about the code. For now, I'm just going to cover the general structure of a tree node. It's pretty similar to a linked list node where we have a few properties. One is going to be the value. In this case, it's an integer, but it could be anything else. And also, we're going to have a couple pointers, which could be different based on the language that you're using. But in general, they're going to point at a couple tree nodes, the left and right child. Initially, they could be set to null. And to add a child node, you would simply reassign this to the child tree node. And generally, when you create a tree node, you want to, at the very least, initialize whatever the value happens to be. So the value for this tree node, of course, is 2. The left pointer is pointing at this node. The right pointer is pointing at this node. So now we have a decent understanding of the basics of binary trees.
Very low key video today, but 1 minute left. Thank you for watching first. Big up on yourself. Today we're gonna run, but at least we finish the hour with running interspersed with walking, guys, and the pressure from the run in a long half marathon. So we're there from 21 kds today to 2K today. It's just like go something. Wait, 2K? Oh no, this round. Oh, I guess because of the treadmill. Yeah. Um, this is probably around 4K, 4.5. So yeah, from 21 to 4. But we're still outside, right? Got it? Get it? Thank you so much. Tune in. Big up for the support. I hope you learned something today. You learned about binary tree and the bucket search and how to search a 2D array. All right? Yeah, man. Big up on yourself. Big up Neetcode. We're running and we're watching. Bless up himself. All right, cool. Bless him. Amazing.